Hello and welcome to our discussion on adding and subtracting decimal numbers. By now you understand whole numbers are written in a base 10 format where each digit, right, in the number denotes a higher power of 10. The ones digit is really 7 times 1, but 1 is technically 10 to the power of 0, right? And then the 3 here represents 30, which is 3 times 10, 10 to the power of 1, right? And the 2, this is 200, represents 2 times 100, which is 10 squared. So you can see everything is based on powers of 10. Well, that same pattern holds if we go to the right and go past the decimal place to the right and start getting into, pieces of whole numbers. And that first decimal, called the tenths, is 5 times 1/10, 1 over 10. And that is 10 to the negative 1 power, right? And then this is 7 hundredths, which is 1 over 100, which is 1 over 10 squared, which is 10 to the negative 2. And this, of course, can be 10 to the negative 3, negative 4, and blah, 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 blah. It's an even easier pattern because here we have 10 to the 0 and then 1 and 2. So everything's kind of off by 1 as far as the first digit has a power of 0 on your 10 and the second digit has a power of 1. But down here, the first digit has a power of negative 1 and then negative 2 and then negative 3. And you can remember it's negative because we're going to the right? You can almost think of the decimal point as being that, the vertical y-axis on the number line where 0 is, and everything to the right of it is negative, and everything to the left of it is positive. So there's some nice patterns to these things. You've also seen decimals all the time because you've dealt with money, right? And the cents portion of the dollar is money. And we know that the first digit is times 10, right? So we get 70 out of that. And then the second digit is times 1 for pennies. Now, writing decimal numbers in words, right? We don't have to do a lot of this, but again, it comes back to these simple powers of 10. You go tenths, and then 10 squared is 100, so hundredths. And then 10 cubed is 1,000, so thousandths. You can see that all we're doing is adding the THS to the end of them to denote that they are pieces of those things. So instead of being tens, right, being 10 like whole things in powers of tens, it's tenths. It's a piece of a 10. It's 1/10 of something. So we can look at, 0.6 and say that's 6/10. 0.05, right? Since the 5 is in the second place, that's 5 hundredths. Then when we get 0.267, you get 267 10,000s. You'll notice that we don't go 2/10, 600ths, 7,000ths. I mean, technically that's what we have, but to be more efficient, we just talk about having 267 10,000s because we also technically have that, right? We have that many 10,000s, and if you kind of broke it up, if you did them individually, 2/10 plus 60 hundredths plus 7,000ths, and then had to, do a common denominator to add them all together, you would see that you get the exact same thing, right? Take this and turn it into, multiply it by 100 so that you get 600 over 1,000. Oh, sorry, I'm looking at the wrong one. I'm like, that number doesn't seem right. Sorry, I want to look at 267. So that's really, right, this piece here is 2/10 plus the next piece is 6 100ths, right? And then the last piece is 7 1,000ths, but if we want to add them, we have to make them common denominators. So this one top and bottom by 100, this one top and bottom by 10, and we get 200 over 1,000 plus 60 over 1,000 plus 7, 267, right? So they really do still have their individual fractions, but we can put them all together so we can just give them one name, and it just saves us time. We're just being efficient. Now, normally, when you have a decimal number that's less than 1, meaning unlike these examples here, you don't have anything to the left of the decimal, right? We have 7 here, we have 12 here, but you'll notice both of these, we just have zeros to the left of the decimal because the number as a whole was less than 1. And that is a typical kind of standard operation. So it's really easy to mistake 0.6 for just 6. It's really easy to miss that decimal when you're writing things out. It's much more difficult to miss it when you have that leading 0. So just as a way of making sure that we are being as clear as possible with our answers, we always put a 0 in front of decimals that are less than 1, i.e. that don't already have a whole number value in front of the decimal. Okay, just like before, we have digits, but the things to the right of the decimal number are called decimal digits. Not really important, but when you hear these things called decimal digits, you'll know what they mean. It's just the digits that are to the right of the decimal point. Now, it's very often that additional zeros are attached to a decimal number, and we can do that without changing its value. So we can write 8.5 as 8.50 and 8.5000 and so on and so forth. The reason why you will see extra zeros added to the end of a decimal number is it's basically telling you the level of accuracy of that measurement. If you see 8.5, all you know is that number is accurate to the tenths place. It could have been 8.54, right? And it still would have rounded down to 8.5. But when you put 8.50, now you know that it's accurate to the tens place and it's been rounded to the hundreds place. And so on and so forth, right? So 8.5000, we know that these first 3 are all accurate. So it's accurate to the tens, hundreds, thousands place. And then this could possibly have been some rounding. So it basically gives you kind of degrees of accuracy by adding zeros to a number. Now, you can't just add zeros to a number willy-nilly. If you actually have a number that you're calculating and it comes out with a high degree of accuracy, then you can put those zeros in. You can also leave them out, of course, if you don't need to convey that extra level of accuracy. So we can remind ourselves again that these things are all broken up into pieces, so we could write it in an expanded form. I don't know why we would ever want to do this, but it's nice to know that it does exist. It just reminds us that everything is powers of 10. The names of things, right? I think we're getting used to the ones, the tens, the hundreds, and the thousands. Well, on the other side, we just have the tenths, hundreds, thousands, and 10,000s, right? Everything just has that THS at the end of it. And because decimal numbers represent fractions with denominators equal to powers of 10, adding these things is really easy because all you have to do is, multiply by various powers of 10, like I showed you in the previous example of being able to take that decimal, write it out in all of its individual pieces, multiply it by whatever you need, and then you can add and subtract. But we're not going to do that. Instead, we have to worry about, well, how about adding and subtracting actual decimal numbers? Again, that's really easy too because we just have to stack them and add just like we would stack and add any other two sets of numbers. And if you're going to add, let's say, 3052 plus 407, you're going to stack the 407 here because you want the ones to be in a column, right? The tens to be in a column, the hundreds to be in a column, and the thousands to be in a column so that you can add straight down. Well, it's no different with decimal numbers. So when you line up the decimals, that's the easiest thing to kind of clue into. It automatically forces everything to be in the proper spaces so that you can add your columns like you would anything else. So adding these is no different than adding whole numbers. We have just added in some extra numbers to the right of the decimal, but the rules don't change, right? You still stack the like digits, then you add vertically. 0 plus 7 is 7, 2 plus 5 is 7, right? We have a decimal point, so we put a decimal point there. 3 plus 1 is 4, and 1 is 1, nothing happens there. And just like before, we can have carryover, right? You can do 5 plus 0 plus 0 plus 5, that gets us 10. So we put a 0. We carry the 1 up here. And then 1 plus 7 is 8, right? Plus 5 is 13. Plus 7 is 20. Plus 4 is 24. Put a 4 here, carry the 2, and then add these all together to get 40. So the whole carrying aspect of addition and the whole borrowing aspect of subtraction all remain the same regardless of whether it's a whole number or a decimal. Again, we line everything up. 6 minus 0, that's easy. 5 minus 0, that's easy. 7 minus 1, that's easy. 3 minus 4, we can't do that. So we borrow 10 from the 4. We turn that into a 3, which makes us a 13. 13 minus 4 is 9, and this is still a 3. You can see that it doesn't change at all. And if we had to borrow from decimals, that would have been the same thing as well, right? So let's look at this example. We got to go 0 minus 7. We can't do that, so we have to borrow from the 2. It becomes a 1. This becomes a 10. 10 minus 7 is 3. 1 minus 1 is 0. Move over here. 5 minus 6. Darn it, it's too small again, so we got to borrow from this one. It becomes a 3. Then we got 15 minus 6 is 9. The 3's cancel to give us a 0, and we move on, right? So it doesn't matter if we have to borrow from the decimals or if we have to borrow from a whole number. It's all the same. Even if we have a whole number and we're subtracting a decimal from it, well, we basically need to borrow from that whole number, turn that into a 5, and then change this into a 1, right? But we need to get numbers all the way out here. So we cancel that, borrow over, cancel that, borrow over. We finally can do our math, right? So it's really easy to do all of this by hand, but it's even easier to just do it in the calculator. Just take some technology, do 36, subtract this from it, and you'll get your answer. But just realize that if you had to do it by hand, or if you want to understand the mechanics, you're still borrowing like you normally do. All right, here's another example. If you want to read through it, you can see it's just borrowing again. Nothing really changes, and that's all I have for you.